In section 8.3, we're going to discuss another shape that's very similar to the ellipses we were just looking at, and it's going to start off in the same way. We're going to begin with identifying the components of the shape and looking at how to draw the graph of it. So you don't have to write down the applications in your notes, but just to show you a quick idea of what the shape looks like, we still have a center, we still have two vertices, and then we still have the foci that the kind of parabola shapes are going to be approaching. That was the same idea with the focuses last time. It's just that before, the vertices were on the outsides and the focuses were on the insides of the shape. So the shape was moving around the foci. It's still going around the foci, but the foci are on the outside. So it splits the graph into what looks like two different parabolas here. What causes this is that now we're not looking at the set of all points whose distance from two fixed points have a constant sum. That's what the ellipse did. The sum of the two lengths added up to the same value. Now it's the difference of the two distances added up to the same value. So a couple applications. Many reflecting telescopes often bounce the light from several of these conic shapes to magnify or help focus the image. Or you could also imagine having something like Earth as one of the foci. And when a comet comes in and gets affected by the gravitation of Earth, but does not get stuck in a loop orbiting around it or actually crashing into it, it just pulls itself off its track a little bit and then shoots off another direction. It follows a hyperbola path rather than a parabola or an ellipse. So here's the standard form. It should look almost identical to the ellipse one. We still have numbers being added and subtracted from the x and the y values. That's how we'll find the center. We still have a number squared underneath each of those. We still have the equation set equal to 1. The difference is that now it's a minus sign in the middle instead of being a plus sign. And that's what caused the difference I was referring to on the previous slide. Now it's a set of all points whose distances from two fixed points have a constant difference instead of constant sum. Now on the last shape, I told you it really didn't matter. I usually liked having the a squared value first for the ellipse. With this shape, it does matter. Addition was commutative, so we could switch the order of the two terms and it really wasn't that big of a deal. But now that we have a subtraction sign in here, you cannot just rearrange those. So make sure that you're always identifying a squared as the first denominator. It's not necessarily the biggest one, it's just the first one. So look for the positive term and put that one first, whether it's x or y. So if that positive term, that first one, is underneath the x, then your hyperbola shape is going to be opening left and right. And then the foci will go in those same directions. The formula for finding the foci has changed a tiny little bit, so make sure you are noticing the difference between this one and the last one. Now we have c squared equals a squared plus b squared. So add those two denominators together, and that will be your c squared value. You can take the square root of that, and that'll give you the distance to the foci. Now, there kind of are asymptotes in this graph. We're going to sketch those asymptotes using the a and the b values. Now, we don't draw the asymptotes into the shape a lot of time, but they are creating what it looks like. So the a and the b values that you get from the bottom of the two fractions, we're going to create a rectangular box out of that, and you'll see that in a little bit. And then that's what I'll be referring to if I ever mention the asymptotes of the hyperbola. Now, before we had the major axis and the minor axis, very similar, they just changed the terms. Now we have the transverse axis and the conjugate axis. So just like before, the lengths are 2a and 2b. So the primary distance, the a value distance across, is the transverse axis, just like we used to call that the major or the long diameter of the ellipse. And then the conjugate axis is the other one. It's perpendicular to that. That's going to be the length of 2b. So it'll be the one that has a negative sign in front, whether that's the x or the y. It's whichever one comes second. So let's go ahead and start with examples. Now, sometimes it'll already be in the form you need, and you won't have to deal with the first couple steps I'm going to show here. But in this specific example, right now it doesn't match the formula I just showed you. So we're going to do a little bit of solving. Basically, we need to get the right-hand side equal to 1, and that should take care of everything. So in this case, right now I have set equal to 36. So I'm going to divide all three terms here by 36. And that first piece, if you reduce the 4 over 36, you're going to have x squared over 9. And then 9 over 36 will reduce to be 1 over 4, and 36 over 36 will equal 1. So now it matches the form of what we were looking for on the previous equations. Now, when the questions ask you for the vertices, they want that a distance, in this case, going to the left or to the right, because my equation starts with an x. If it started with a y, I'd be going up or down that distance. But in this case, I want to go from the center, and I want to go left or right a. So notice that a squared is equal to 9, which means a equals 3. And since I said that this one is starting with an x value, I'm going to go to the left or to the right that 3 distance. So in this case, I'm even okay with you just writing plus or minus 3 comma 0, or you could write negative 3, 0 and positive 3, 0. That would be fine. Next is the foci. Now, to find the foci, I did point out that the equation has changed a tiny little bit. Now we're going to take the sum of the two denominators, a squared and b squared, and then we're going to take the square root of that to find c. So in this case, the c squared value equals 9 plus 4, which is 13. And then if you take the square root of that, you get the square root of 13. You can't reduce that, you just leave it as a square root of 13. So they're not pretty numbers, but we're going to say that the foci, it's going to go in the same direction that the vertices went in, so it's going to be plus or minus square root of 13, comma 0. Again, I'm just starting from the center, and then I'm going that length of c in the same direction that the vertices went in. Because if you look back at the original graph, the vertex and the focus lie right next to each other. They should all be on the same line, all of the vertices and foci. So now we've labeled the center, the vertices, and the foci of the shape. So let's talk a little bit about how to sketch them. As I said, you're going to be using the a and the b values to kind of outline some asymptotes, and then we're going to create the hyperbola shape around those. So let's focus on the case where x squared comes first. So we have x squared over a squared minus y squared over b squared equals 1. And if you're doing the other case, it would just be a matter of flipping whether you're going left and right or up and down in the separate cases. So first, you're going to use the a value in the x direction. So you would go right a, left a, because we just said that those are the lengths to find the vertices. So left a and right a, you would draw 2 dots. Then you would use the b value, and you would go up or down b in this case, because b is underneath y. So up b and down b from the center. So you draw those 4 points, and then using those points, you're able to sketch a rectangle around them. Now, once you have the rectangle drawn, you're going to put diagonal lines going through the corners of that rectangle. So you should end up with a shape that looks like this. The equation of the asymptote ends up being b over a and negative b over a. That's not too important. I don't think any of the questions on the assignments will ask you for that, but if you wanted to see what the equation of that straight line was, that's the slope-intercept form for it. And then the last piece, we said that the a length is actually one of the vertices of the shape, so the graph actually touches at that point. And then remember, your graph approaches the asymptote, but it never actually hits it. So you can sketch in a parabola shape that gets closer and closer to those asymptotes, but never touches it. So a very similar process can be used for the up and down shape. You would just be going up a and down a, because now your a value is underneath y, and you would be going right b and left b, and you would use those values to draw your box, sketch in your diagonals, and then the most important thing would just be to remember that since this is a y squared equation, you're actually using the top and the bottom of the box instead of the left side and the right side of the box to sketch it. So let's do a couple examples practicing that. Now this first one, we probably don't need to draw the box in ourselves since it's just a multiple choice question. They just want us to match. Do note that the center is at the origin. It appears to be going around the origin of the shape. So I shouldn't see any numbers being added or subtracted from the x's or the y's. So I'm just going to go ahead and cross out those 2 answer choices. Okay, out of the ones that are centered at the origin, they don't have numbers being added and subtracted from x and y, I need the one that's going up and down. So the up and down case is the one that starts with a y squared value. The y stuff is the positive term and the x stuff is the negative term. So that means my correct answer choice has to be this choice B. If you needed to be more specific, if there were two more similar answers than this, you could also recognize that from the center, the graph is going up and down 2 because the square root of 4 is 2. So from the center, it does appear to be going up 2 and down 2. And then it's a little bit harder to see the other value, but if you sketched in the box going right 3 and left 3, since the number underneath x is bigger, that does seem to make it a little bit wider than it is tall and skinny. So now let's practice sketching one on our own. First, we want to identify the center of this graph. In this case, it's going to be the -3, +1 value. Don't forget to change the signs because the formula has minuses. So subtracting h, subtracting k. So I'm going to go left 3 and up 1, and I'm going to draw the dot. So that's our center. Now, in the x direction, the square root of 4 is 2. So I'm going to go right 2 and left 2 from the center. And I'm going to draw 2 dots in there. And then in the y direction, the square root of 9 is 3. So I'm going to go up 3 and down 3 from the center. And so like I said, I just start with those dots, and then hopefully you can see how to sketch in the rectangle going around this. Just make perfectly horizontal and vertical lines and stop once you would hit one of the other lines. So our asymptotes would be going through this diagonally. In fact, let me do that as a dotted line instead, because this is not actually part of the hyperbola itself. And so we have our box drawn. The last thing you want to be careful about is should the graph be going left and right or up and down. This one starts with an x value, so it's going to be the left and right sides that we're using. So the value that starts on the right side of the box, that one is going to approach the asymptotes but never quite hit them. And even though it goes off the graph a little bit on the other side, that's fine. We can still sketch the graph in over there as well. So that is our shape of the hyperbola. Beautiful. So that's all for the notes today. Thank you guys, and good luck on the assignment.